Okay, yeah. So, as I asked you before, it would be nice if you don't mind turning on your video because it feels sort of surrealistic to speak to my laptop. I feel a bit on the eccentric side. Thank you. Okay, one comment that the university rules sort of guide me to do is to let you know that all classes are recorded. And formally, a student can object to recording, but I'm not sure I know even how this can work because there are students who take this class not in a synchronous basis. So they need the recorded version. So I'm not even sure I understand the university rules. So let's keep it simpler. I just notified you that this and all other classes are recorded. And if you have any misgivings about that, let me know and I'll try to work it out because I really don't know how I can both record and not record things at the same time. Okay, so you know, there's these funny rules that are derived from privacy laws that are taken to a limit, in my opinion, but just for you to. So I actually now have it on record that I told you that the class is recorded. Okay, so what we are going to do today is we are going to go back to the slides, and I'm going now to the share screen. Where is that? Just a second. Just a second. I'm a bit puzzled by the reason that I don't find my slides here. Second, I don't understand where my slides are here. Okay. Okay, sorry. So, okay, so here we are. We discussed several recurrences. This is the simplest recurrence that we already saw a couple of times and we are going to see again later in this class. It's T of n equals to 2 of T of n over 2 plus n. And what is remarkable about this recurrence is that, as you see here, where we start expanding it, what we get is at the first level, we get an n. In the second level, we get another n, because we get here, when we expand this to the T of n over 2 to 2 of T of n over 4, we get an n over 2 on the side, and when we multiply it by 2, we get another n. So we get a second n. And when you expand it another time, we get a third n, and so on. So the fact that at each level of the recursion, we contribute the same amount means that because of the depth of the recursion, if we start with n, we end with a constant after a logarithmic number of rounds, because we go from n to n over 2 to n over 4 So we go down geometrically. So the depth of the recursion will be logarithmic. Each level will contribute an n, so we'll have a total of n log n, which is the solution of this recursion. Now we are going to see why this particular case is a middle case between two extremes. In one extreme, only the top level of the recursion will affect the result, meaning if we'll have here some f of n, only this will appear in the solution for t of n, and this will go away. And in the other extreme, this will go away, and the only thing that will appear in the solution will be the number of leaves once we expand the recursion and the contribution of the leaves. So this will be the two extremes. Now, in order to get there, we considered this example. In this example, I'm going to use it in a big way in lieu of a proof. So I'm not going to go into the full formal proof, but I'm going to use this example because it is so telling. And we went over this example. In this example, we have a recursion of t of n equals to 3 over t of n over 4 plus cn square. And for simplicity, we are going to assume that n is an integer power of 4, meaning there is some integer k where n is 4 to the k. This will make our life simple. Now, what is going to be the most significant thing that you should train yourself to see immediately upon looking at this recursion? So I'm giving you sort of a heads up towards the theorem. It is that the recursion calls, the call of the recursion is to a term which is n over 4. So we go by a factor of 4 down at each level of the recursion. However, while we go by a factor of 4 down, we multiply by 3. So what is the main thing to notice here? The main thing to notice here is that 3 over 4 is less than 1. And we are going to see why the fact that we have here that it's a huge difference due to the between having here 5 of t of n over 5, where 5 over 4 would be larger than 1, or 3 of t of n over 4, where 3 over 4 is less than 1. So the fact that we have a 3/4 situation here, instead of, which is a smaller fraction than 1, is going to be the major thing we need to take into account when we consider the behavior of this recursion and its solution. And where do we see it? We saw it in this figure that we visited at length in the last class, where what we observed is that when we expand the recursion, we get here first a 3-fold expansion, then a 9-fold expansion. And when I put here on the side all the things that are left on the side, so first we have a c of n square, because this c of n square is coming from the top. Then as I come down, I have here n over 4. And since the quantity that is contributed is whatever n you have, which is n over 4 square, and we have 3 of them, the contribution of this level will be 3 over 16 times c n square. And you can immediately see that what we are going into is a geometrically reducing term, and therefore it will be dominated by the first term. Okay, so that's the main thing to observe. And the other thing that we observed in this slide is that you can express the leaves as a factor, as a power of 3. And in this case, it will be 3 to the power of log base 4 of n. I hope that this is clear. And what I guided you to observe is that this term is equal to n to the power of 3 to the base 4. And why are they equal? It's very trivial. It's a trivial observation. You just take the logarithm of both sides, and you can immediately see that they are equal. Okay, so this is a summary of what we discussed up to the last class. And now we are going to extend it into the theorem. Before we are going to do that, we observe that even if we have a situation where you have a recurrence of the form T of n equals to T of n over 3 plus 2 T of 2/3 of n plus C of n, then we are basically in the same situation as this situation. Because when we start expanding the recurrence, we are still going to get a linear term at each level of the recurrence. And the way we see it here is right here. The first level, we have C of n. Second level, we break into two uneven terms, C of n over 3 and C of 2 of n over 3. But each of them contributes a factor which is linear in its size. But since they sum up 1/3 and 2/3 to 1, we get another C of n. And then as we expand in a Breadth's first search type manner, we get a linear factor at each level. And what is going to be the maximum depth of this tree? The maximum depth is going to be logarithm, but the base of the logarithm will be 3 over 2, right? Because instead of coming up by a factor of 2, this is going to be the longest path to a leaf. Is that clear? Because the others are coming down much faster. But I don't care if some of the others will reach the leaf level earlier, because even if I penalize myself and say every level will contribute C of n, we are still going to have no more than big O of log n levels. And for that reason, the solution will be order of n log n. Okay. So now comes the master theorem. And while I'm not going to prove it, I'm going to relate to it and explain it in the context of the examples that we saw so far. So the master theorem does not consider all possible recurrences that we saw so far. For example, the last recurrence where T of n breaks into T of n over 3 plus T of 2/3 of n is not captured by the master theorem. So the master theorem captures only a limited number of recurrences, but it still captures them in a generic way because it allows you to describe the recurrence using a more general placeholders such as the letters A and B here. So consider a recurrence of the form T of n equals A times T of n over B plus f of n, where both where A is larger than equal 1 and B is larger than 1. The B larger than 1 guarantees that we keep coming down here. Otherwise, it's not clear that we are even converging. And the one thing that I was asked in a prior class is that what is being assumed here all along is that T of a constant is a constant. Okay, or T of 1 is 1, or T of a constant is a constant. And remember that our interest is to solve everything up to the big O notation. So we are not trying to resolve or solve recurrences up to a constant factor, up to an exact solution, but rather up to a big O, the big O space. So if f of n is upper bounded by something which will basically looks like order of n to the power of a over to the power of n to the to n to the power of the logarithm base b of a minus an epsilon. So the minus epsilon is not is separate. So imagine that you have a parenthesis around this, and this appears on the side. So it is an order of magnitude below the value of order of n to the power of the logarithm of a to the base b. So to the extent that you can point at some constant, then it means that basically that the f of n is playing a minor role, and the solution will be the total number of leaves. And this is exactly the type of case that we saw in this example. So convince yourself that we are in this case where the number of I'm sorry, let me take it back. I'm sorry. No, we are exactly not in this case. I apologize for that. I'm sorry. So this is the case where what happened is not what we saw in the prior case, because the number of leaves is going to dominate. And a very simple example where this will happen is this type of an example. Consider a recurrence of the form t of n equals 4 times t of n over 2 plus n. So what will happen here, you can convince yourself that the number of leaves will be this, and this will be the solution. And you can do that by just plugging it in this formula. So this is the case where the number of leaves dominate. This case is where f of n and the number of leaves are on the same order. In this case, we have the extra logarithmic factor. This is exactly the case we saw here, where the number of leaves evens out with this n, and for that reason, at every level, you have an n contributed on the side, and what you have in the solution is either the number of leaves times log n or f of n times log n, because they are equal, so it doesn't matter. I hope it's clear to you that here I could have replaced this term by f of n because they are equal. Okay. And the last case, which is the case that we saw in the diagrammatic example, is where f of n is at least the number of leaves plus an epsilon. And in this case, what will happen is that the f of n will dominate because we are going to run into a situation of a geometric sum. And that's the same situation that was demonstrated in this example. Now, you may want to ask, but what happens in cases where I have the same recurrence as here, but we are between these two situations? Meaning, I cannot point at an epsilon that will allow me to say that f of n is here. Maybe it is some term that maybe less than a constant that separates this from this or here. In this case, the master theorem does not tell you anything. Okay, so it's important that you understand the limitation of the master theorem, and overall the best way to remember it is that we have here these two terms, the n to this power and f of n. And what is the question? The question is f of n smaller asymptotically, or significantly smaller asymptotically? This is case 1. They are about equal asymptotically. This is case 2. F of n is larger asymptotically. This is case 3. So that's basically the master theorem. Any questions about the master theorem at this point? Okay, so we can move on. And the next thing I wanted to refer you to is to this appendix, which when you see such a slide, it means that you are responsible to read it and understand it and know the material. Now we are going to advance to something which is really cool. So we learned already quicksort, but quicksort has something truly arbitrary about it, because quicksort is all about, if you remember, about finding or declaring a pivot. Once you declare the pivot, everything is automatic. You have a bunch of elements that you need to sort. You pick one of them, you compare everybody to this item, to this element, and some are smaller, some are higher, and you continue on each group separate. Okay, that's the whole idea of quicksort. But if you pick the element in an arbitrary fashion, nobody guarantees you that you're making a good choice, because maybe you're selecting always the largest element or the smallest element, and then you don't get any partition. And we already explained why the worst case behavior of quicksort is n squared, which is as bad as you can get in this type of sorting algorithms. Because think about it. What is the worst case you can do when you have a sorting situation? You can compare everything. So this is n squared. So this is the dumbest solution in this space, where you just compare everything, and clearly n squared is not good enough. So what is the basic idea here? The basic idea is to use something which is a really pretty authentic computer science idea, but it requires a discussion, because many of you come from electrical engineering. And one of the things which are, I believe, typical to electrical engineering is the tendency to assume that inputs come from a random source. You don't know anything about the input, but often people are making this type of assumption in communication, sometimes in control. But we have absolutely no reason to make this assumption for sorting in general, because sometimes we get input which is almost sorted. You know, you get a bunch of items, like the students, say the students that registered to University of Maryland last year. So suppose you already sorted them, and now you add the students of this year. So assuming that only maybe a quarter of the students are new, 3/4 of them are already sorted. So you cannot assume that you get the list of students initially completely unsorted. Okay, so people in computer science have felt very uncomfortable about this assumption that inputs comes from random sources. Now, so what is the next idea we can come up with? And here is where I'm trying to communicate with your mathematical intuition. So the question is, how can I still apply probabilistic analysis to a situation where I cannot make an assumption that the input is random? And here comes the idea, which is, and the key term to remember here is randomized as opposed to probabilistic. Okay, so when people use the term probabilistic, they tend to, the convention, at least in computer science, is to assume that the input comes from a random source. And as I said, in computer science, we try to avoid it. What is the idea of randomized? In randomized algorithms, what we do, we assume that the computer can toss the coin. So it's not that we are making any assumption whatsoever about the input. Okay, so we are tossing a coin, and the coin is under our control, and whether a deterministic computer can toss a coin or not is a whole big philosophical question which is beyond the scope of this class. But let's assume that the computer can toss a coin. Okay, so I'm making this assumption. So we are sidestepping the question of how can you do such a thing in a computer. So there is an enormous literature on that. So we are assuming that the computer can toss a coin. And now we can fully defend the assumption that we can apply probabilistic analysis. Why? Because we controlled the probabilistic, the random variable which is at play, because we are the ones who generated the randomization. So what will be the basic idea here? The basic idea, as you remember, the key routine in quicksort is what's called partition. And what's going on in partition? In partition, what's going on is that we look at a subarray. So originally, we want to sort the elements in array A that had n elements, but extending from location 1 or index 1 to index n. But as we do the recursions, we reach a subarray that starts at location P and ends at location R. Both are integers, and R is larger than or equal P. And then let me remind you what's going on here. So in the prior application of partition, we just did partition where they used as a pivot the element in location R. Here we do something else. We do something which is a bit awkward, but instead of looking at what is written here, I'll tell you what we do, and then I'll show you how we implement it. So the idea is, instead of insisting that the pivot will be the element in location R, which is arbitrary, we pick a random elements in the range P to R, and we declare it a pivot. Okay, so now we have any element in the range between P and R in the subarray can be the pivot. But because we or the book or the people behind the book are lazy, what they do is the following. They pick a random index in the range from P to R, and then what they do is they exchange the element in location I with the element in location R, and now the new pivot is in location R, so they can apply the prior partition. Okay, so they were just too lazy to rewrite partitions, so you know, they reduce the problem to something they have solved before. I'm sure that many of you have heard the situation of how a mathematician boils a kettle of water. So basically, the mathematician uses to have the kettle in his living room, and then when he wants to boil the water, he takes it to the kitchen, put it on the fire, and boils it. Okay. Now, one day he wakes up and he finds the kettle in the kitchen. So how should he boil water? So any reasonable person would take the kettle and put it on the stove and boil it, right? But no, the mathematician would take it first to the living room, because from there he knows how to solve the problem. Okay, so the point here is that you reduce it to a problem you have solved before, even if it's a roundabout way. So that's a lazy solution, which is exactly what is done here. Not very logical, but correct. And in terms of our complexity, when we care only about a big O type complexity, we are not penalized for this silliness. Okay, so now what is a randomized quicksort? Because we here explain randomized partition. In randomized quicksort, we asked like the usual termination rule. If P is less than R, because if P equals R, we are done. Then what do? We call randomized partition. Here is the index, the ranking of the pivot, and here we continue solving it by calling recursively the elements smaller than the pivot and larger than the pivot. So that's the whole idea of randomized quicksort. It's the same old quicksort with the added step of choosing a random pivot. Any questions about randomized quicksort, about the algorithm? Okay, so if there are no questions about the algorithm, I'm now proceeding to the new element, which is a analysis of a randomized algorithm. And the analysis will be a randomized, a probabilistic analysis. And our objective is to figure out the expected runtime of this algorithm. I hope that it is clear to all of you that the worst case runtime is as bad as before. But now it's meaningful to talk about an expected runtime because we have a probabilistic model in which we can argue about the probability of various events. Okay. So what is the lead observation here? The lead observation is that in order to figure out the runtime, the only quantity that we need to reason about is the number of comparisons that are performed in line 4 of partition. So let's go and figure out where is line 4 of partition. So I'm going back where we first saw the code for partition. It was a while ago. Let me see. Yeah. Okay. So this is the partition. So let's see what's going on here. This is still the partition which doesn't show the randomized selection of the pivot. It's the part that we maintain as it was before. So let's see what's going on here. So what we do here is that we put the pivot into X here, and then we go and compare all the elements to the pivot. Okay, here we go and compare all the elements to the pivot, and finally we exchange the pivot with its proper rank. Okay, so what's going on here in terms of comparisons is that if you give me a piece or a subarray of size R minus P plus 1, this is the total number of elements here, how many comparisons do I do? The answer is basically R minus P plus 1, right? Because everybody is compared, or R minus P, everybody is compared to the pivot, and then we do some extra operation. It doesn't matter. R minus P is good enough. It doesn't have to be the plus 1, because we are interested here. We are interested here in the in the big O type of things. So let's try and reason about what would be a good situation. A good situation is if when we start with quicksort, we break into two even pieces. Say the first pivot is the guy in the middle. So in the very first round, we would do n comparisons because the partition for the beginning is A1 up to n, right? Because that's what we get in the beginning. And then suppose that in the best scenario, for the left side, it will be A1 up to n over 2, and for the right side, it will be n over 2 to n. And then what we will do on each side, we will do n over 2 comparisons, because this will be the size of the pieces. The left piece will be half, the right piece will be half. And then we hope to break exactly even, and then every level will require another n comparisons, but since the depth will be log n, it will be n log n. Now, what will be the worst case? The worst case is where we keep picking, say, the largest element for pivot, and then in the first round we'll do n, second n minus 1, then n minus 2 comparisons, and so on. So it will be n squared. So what we see is that what really matters is the comparisons that are happening with the pivot. And here is the point where we are going to take this and apply it or incorporate this insight into our analysis. Okay, so the total number of comparisons is X, and that's what we need to account for. So the question is, who will be compared to whom? So first, we need to observe that what will not change, no matter how lucky you are with the pivot, is the number of calls to partition. This will be n minus 1, because, think about it, because in each call you actually rank one element, and we need to rank a total of n elements. So you need n minus 1 calls, because the last element will be ranked by default. So it's basically n calls to partition, n minus 1. So what will be the total number of comparisons that will take place? So here is very elegant analysis that does the trick for us. So what is the basic idea behind the analysis? The basic idea behind the analysis is that we are going to do a trick which you cannot do in an algorithm, but you can do in analysis. What can't you do in an algorithm? In an algorithm, you cannot ask, let me start with the solution, because that's what you are looking for, right? So you cannot say, give me the solution when your problem is to find the solution. But in an analysis, you can ask, let's start with the solution and see how the algorithm will approach the solution and will incorporate it into its flow. So here is the idea. The idea is to think about the output solution, output array, where everything will be sorted. So in the output array, we can assume that we know the order of the elements. Z1 is the smallest, Z2 is the next smallest, and Zn is the largest. Okay. Okay, next observation or next notation is to define, to use what's called, I write here X, but it's the Greek letter chi. And chi is used as an indicator random variable, chi ij, and chi ij will denote, it will be a random variable that will mean that is Zi compared to Zj. So this will be the question. Is Zi compared to Zj? And the random variable will get the value of 1 if they are compared in a particular run, and 0 if not. And because what determines the complexity of the algorithm is the number of comparisons, which is x. What is x? X is in fact the sum of all pairs, or xij, because we have a total of n elements. Some will be compared, some will not. The ones that will be compared, each comparison will happen once, it will contribute 1 to its indicator random variable, and the sum in a given run of xij will be the x we are looking for. And the question we are asking is, what is the expected value of x, which is the sum of the indicators? In other words, just to state here what we are talking about by opening and just restating what our definition, we are asking to do the sum of all pairs where the probability of whether Zi is compared to Zj is the quantity that we sum up. Is that clear to everybody? If you have a question, please ask now. Okay, so I'll assume that this is clear. And now comes this very elegant way of reasoning about this probability. So Zi and Zj will be compared. When will they be compared? So look at two indices, Zi and Zj. And we are assuming that I is less than j without loss of generality. So in what event will Zi and Zj be compared? So I hope it's clear to all of you that if you give me two values, Zi and Zj, where Zj is larger than or equal Zi, there is a certain subarray in the output that extends from Zi to Zj, Zij, capital Zij, that starts with Zi and goes to Zj, and all the elements here are non-decreasing. Okay? Now, here is a very simple observation. At least one, either Zi is compared to Zj, or there is some element between them that is chosen before them in the choice of pivots. So just think about it. In the beginning, we don't know, we have not yet seen any element between Zi and Zj chosen as a pivot. As the algorithm runs, there got to be a point where some element in this subarray will be chosen as a pivot. We don't know if it will be Zi, it will be Zj, or some element in the middle. But clearly, the algorithm cannot run to the end without choosing at least one element in any of the output subarrays. Because if we didn't choose anybody here, we never compared, and we have no way to actually have concluded that we did the sorting, and the sorting would be incorrect. So there got to be some point where some element in this range was chosen as a pivot. It can be either Zi, some element in the middle, or Zj. There is only, among all these possibilities, so in this range, how many elements do we have? The answer is j minus I plus 1. J minus I plus 1. Now, among the possibilities of choosing any of these elements as a pivot, under what possibilities will Zi be compared to Zj? If Zi is the first element to be chosen as a pivot, everybody will be compared to Zi, including Zj. So if Zi is the pivot, is the first pivot in this range, there is a comparison. Similarly, if Zj is the first element to be chosen in this subarray throughout the algorithm as a pivot, then everybody will be compared to Zj, in particular also Zi. But what if an element between Zi plus 1 and Zj minus 1 is selected as a pivot first? Will Zi and Zj be ever compared in this algorithm? Answer, no. Okay, so this is a very significant observation, because the way in which we declare the choice of a pivot to be of equal probability as we go gives equal probability to any element in this range to be selected as the first pivot in this range. Okay, I hope that this is a very important statement, so I'm going to repeat it. The way in which we choose random pivots brings about a situation where the probability of first choosing any of the elements here as a pivot is equal to any other elements here. So any element here, the question is which one will be chosen first in this range. The answer is equal probability for any of the j minus I plus 1 elements. How many elements do we have in this range? The answer is j minus 1 plus 1. How many of these choices will result in a comparison of Zi to Zj? The answer is 2 out of 3. Why 2? Because only in the case where Zi or Zj are first chosen as pivots, there is a comparison between Zi and Zj. But in the remaining cases, somebody else will be chosen as a pivot. And for that reason, in the other cases, there will be no comparison. Okay. So now we are going to take this. Sorry. Yeah, excuse me, just a second. Yeah, I apologize for that. My grandchildren are visiting. My grandchild decided to express himself. So I apologize for that. Okay, so let us continue. So now that we have a clear idea of the probability of comparison Zi to Zj, and we have a closed term for the probability, what is the next question? The next question is to figure out what we spoke about earlier, right? Which is the expected value of the sum of all the pairwise indicators, Xij, which is the sum of all the probabilities of comparing a Zi to a Zj over all pairs. Okay, so that's exactly what we wrote here. And what remains now to be done is no more than a nice reduction of this problem to a problem that you actually probably have seen in your calculus course. So let me explain. We have here the summation of all the pairs. So the basic idea here is to arrange it in such a way where if you fix an I, and now you look at all the larger J's that follow from it. So think about it. If you give me a given I can either look at the I plus 1, I plus 2, I plus 3, and so on. And in each case, I need to take 2 over the gap between them and sum up. So, and I do it for all the i's. So for every given I take 2 over a gap, and the gap, it may be that it's the next element to me, or two elements away from me, 3 elements away from me, and so on. So the sum that we will need to do n times is 2 over k plus 1, where k goes from 1 to my horizon, which will be n over 2. In fact, it can be a smaller number, but it will never be larger than n or n over 1. Okay, so now I hope that this arithmetic exchange here is clear, because once we have done that, just forget about the 2, because I can take the 2 outside and have now 1 over 2 plus 1 over 3 plus 1 over 4, etc., and up to 1 over n. Now, what is this sum? 1 over 2 plus 1 over 3, ... till 1 over n. Do you remember what it is? This is the harmonic series. And the harmonic series sums up, when n goes to infinity, to log n. I hope you remember that from your calculus classes. So what we have here is summations, and summations where each of them is upper bounded in the limit by big O of log n. And since I have n of them, it will be n log n. And this is the expected value of the runtime of quicksort. Any questions about that? No questions? Okay, so if this is clear, let me just be sure that I see you here. Just a sec. Okay, so now we are going to a next chapter, and the next chapter will be median and order statistics. Okay, so the next chapter will be median and order statistics. And so what is the median? A median is the very simple concept is you have numbers drawn from a fully sorted domain, like numbers, or it can be the students' last names in alphabetic order, and the median is some value that half of the people in the population are higher and half are smaller. What is order statistics? It's a fancy name to giving you the case smallest number. Okay, so case smallest is order statistics. So in particular, the median is the n/2 smallest. The minimum is the 1 smallest, and the maximum is the n smallest. Okay, so that's what the funny name order statistics meant. Yes, I see that somebody asked me a question here. And I saw, I'm sorry, I couldn't see the chat before. We have to compare asymptotic growth of f of n and which other function? Oh, okay. So the other function, okay. So maybe I should go back to this question. Just a second. So let me go to the share screen. Okay. Probably, so what I ask you, if you have a question, please ask it. It's very difficult for me to see the chat during my presentation, so don't hesitate. Unmute yourself and ask the question, okay? So please do that in the future. So here, comparison is of f of n in this function, n to the power of log of a base b. That's a comparison. So I think that this was the question that is asked at the time. If I misunderstood the question, please raise please unmute yourself and ask it.
Yes, that was the question, Professor. Thank you.
Sorry?
That was the question. Thank you. Thank you.
Okay, you're welcome. Yeah, please assume that you please don't ask me questions by chat because it's difficult for me to split my attention, and the way I try to maneuver here sometimes hides the chat, so I don't see them.
Professor, going back to the master theorem.
Okay.
In the previous class, in the recurrence by iterative expansion thing, so we have this equation which is Tn equals to 3t bracket n by 4 plus Cn square. I think,
This one?
This one.
Okay.
So here in Cn square, so is this the first case of the master theorem where Fn is equals to O(n) log A base B?
Let's see.
Like, can we use the master theorem?
Just a second.
Yeah.
You ask the question, you will get an answer. Just a second. No, this is the third case.
Third case, okay. So I don't understand like how it is the third case.
Oh, because let's see. Just a second. Maybe I'm wrong. Just a second. No, I'm sorry. Just a second. Yeah, it's the third case. I apologize. So okay. It's the third case because what you get here is that f of n is larger than the number of leaves.
Okay.
So the key term that you need to note here is omega. So omega means that what you have on the left-hand side is larger by orders of magnitude than what you have on the right.
Okay.
So that's the case where the f of n dominates.
All right. Okay. Thank you, Professor.
Okay. You're welcome. Any other questions? Okay, so let's go to the order statistics thing. And we are going to go through this chapter by way of an interrupt. I'm going to say a few minor things from this chapter, then take a break, go somewhere else and come back here later. Okay, so the first thing that we are going to consider is the following trivial case. Find the minimum. Okay, so how do you find the minimum among n elements? You do the following trivial thing. You take the first element in so you have an array of size n. You take the first element, you put it, you declare it as your tentative minimum. And now you keep challenging it. You compare it to the second element. If the second element is smaller, you declare the second element as your tentative minimum. If the second element is larger, you move, you don't change your tentative minimum, you go compared to the third and so on. So each time you find an element which is smaller, you declare it the tentative minimum. And when you go through all the elements, your tentative minimum becomes your minimum. Okay, as trivial as it can get. How many comparisons did we do here? The answer is n-1, right? Because we, after selecting the first element without a comparison, we compared, we did n-1 comparisons. Now, you don't need much imagination to see that a completely symmetric algorithm could solve the maximum problem, right? Find the maximum element, so you take the first element, you declare it as your tentative maximum, and then you keep comparing, and at the end you remain in your hand with the largest element. And the elegant, not very deep observation here that we are going to discuss next is what can you do in order, if you want to find both the maximum and the minimum. So clearly, you can apply both algorithms, and the total number of comparisons you will do will be 2n-2, right? Because the minimum will do n-1 comparisons, and the maximum will be n-1, together 2n-2. Can you do better? And observe that when we ask, can you do better here, we are deviating from our emphasis in this class on a big O type considerations, because what we are going to see is that we are going to improve the factor of 2 to something better, but it will still be a factor of n. So I want you to align your expectations with what's coming up, because these new expectations are different than what I guided you so far and later. So it's a one-time deviation. So what will be the trick? The trick is that if you want to compute both the minimum and the maximum, what you can do is to advance 2 elements at a time. So what's the trick? The trick is that you take the first 2 elements, you declare the smaller amongst them as the tentative minimum, the larger as the tentative maximum. And now you keep advancing 2 elements at a time. And what do? The first thing you do with the next pair of elements is that you compare them one to the other. If one is larger than the other, what is your immediate conclusion? That the one that is larger cannot be a minimum, because there is already an element smaller than it. And the one which is smaller cannot be the maximum, because there is already an element which is larger than it. So the only thing that remains after you compare the 2 elements is to compare the, the smaller to the minimum, to the tentative minimum, and the larger to the tentative maximum. So look at what happened here. We managed to advance over 2 elements with 3 extra comparisons. While before, we had a charge of 2 comparisons per element, one for the minimum and one for the maximum. So the very simple observation here is that instead of doing a total of 2n-2 operations or comparisons, we managed to get away with 3/4 of it, 3n over 2. Okay, next. So what we are going to do now is we are going to do something which will probably look trivial to many of you, because I'm going to just remind you, assuming that many of you already know it, some classic, very simple sorting algorithms, and then we'll return to this chapter, chapter 9, which is the order statistic chapter. Okay. First algorithm. So the first algorithm is actually known by the name insertion sort. And insertion sort is inspired by the following card sorting idea, where you want you have a bunch of cards that you want to sort. So what do? You first take one card, then you take a second card, and if the card that you took is larger, you put it on the right. If it is smaller, you put it to the left. Then you take a third card and you put it in its due location, either to the right, to the middle, or in the middle, or to the left. And here, the general case is shown here, where I had 4 sorted cards, 2, 4, 5, and 10, and the new card is 7, so I compare 7 to 10, and I observe that it is smaller, so I go to the next location, compare it to 5, and since it is larger, I place it between them. Okay, so this is basically the insertion sort algorithm, and the algorithm is demonstrated on this example, and here is the pseudocode for this algorithm. But what you see here is exactly this general idea, where if this is my original number that I need to sort, I start with the first 2, I compare the 2 to 5, and I exchange them. Then I already have 2 and 5 sorted. Now it's the time for 4. So I compare 4 to 5, I exchange them, and now these 3 are sorted. Then I have 2, 4, 5 sorted. I now take 6, compare it to 5, leave it in place. Now I have these 4 sorted. Then I take 1, and I extend these 4 sorted elements to the 5th. So I compare 1 to this, and to this, and to this, keep changing them, and then 1 is put in its place, and finally I do it with 3, put it in its place, and so on. So the basic idea of insertion sort is actually written here, where we increase an index from 2 to length of A, and then I take a key, which is the next element I consider, first the second, and the third, and so on, and I insert it into the sorted sequence by shifting it down until I reach the location where the element is less than the next key. And then I stop and I exchange it with the key. So that's the algorithm, and that's the insertion sort algorithm. Now, I'm going to say a few things about it. First, the complexity analysis is the following. We are going to ask this question n times, right? Because that's the external loop. Then we are going to do this assignment to key. I'm going to round it. So when I see n-1, I'm going to say n, just because to make my life simple. We are talking about asymptotic behavior. And the first time that things get interested is here, where it's not linear anymore overall, because now the number of steps depends on how many comparisons I need to do. And it is denoted here by T of j simply because I don't know if I can put the element in place because it was the next largest element, or I need to exchange it all the way to become the smallest element or somewhere in the middle. In any case, the observation here is that this T of j is always upper bounded by this value j, and for that reason, it is not difficult to observe that this algorithm is quadratic, because in the worst case, which is the only way we are allowed to reason about it, it can be n squared. And what will be the average case of this algorithm? So the best case obviously will be linear, right? Because in the best case, everything is sorted. So all these T of j's will be just 1. And the worst case is n squared. The average case will also be n squared simply because in the average case, I need to insert an element halfway. So the average case here asymptotically is not better than the worst case, unlike quicksort. So now, one thing you may wonder here, and I think that this is a good time to discuss it, is look at this algorithm. It's really a very artificial algorithm in terms of what you will do, at least in the physical world. Why do I claim that it's an artificial algorithm? Because how would you actually apply insertion sort if you were to sort cards? The first thing that you will do, you will not compare 7 to 10, right? What you will do is you compare 7 to the middle element. Follow me? And then you compare it to these two, and then you put it here. So if now you have 100 cards, you compare it to the middle, to the 50s, and 25, then halfway again. So what you do is basically binary search, which I hope you are all familiar with. So each insertion should take logarithmic time. Follow me? So if in each insertion takes logarithmic time, you may ask, what's going on here? Why am I confusing you? Instead of taking linear time, the worst case, or even in the average case, it should take logarithmic time, and this whole algorithm should run in n log n time. Follow me? So was I wrong to tell you that this takes, in the worst case, n squared? Anybody wants to comment on it? Is it clear that I described to you by hand waving an n log n algorithm?
I mean, the middle part can be the worst case too, even though you are comparing it to the middle. It can be in the way that you have to end up comparing it to all the other values.
No, that's not true. In terms of comparisons, I can compare to the middle, then I will need to compare it to somewhere in the middle of either half, and then in the middle of the remaining half, which would be a quarter. So in terms of comparisons, this is a fully kosher algorithm. Okay, what did I sweep under the rug here in terms of complexity? So I claim that when it comes to comparisons, this is 100% correct n log n algorithm. So why I claim that while I misled you on that, I did mislead you on the complexity of this algorithm.
Could it be with actually moving the elements around?
Good, exactly. Because if you look at how the algorithm was described, there was this shift where if I entered an element in the middle, or suppose that what I did is I compared the element halfway and concluded that this is its location. So I don't even do logarithmic number of comparisons. I do only one or two, if you will. Okay? Sounds great. But then what do I need to do? In order to prepare the elements for the next binary search, I need to put it in place, which means that for that, I need to start shifting the elements one to the right. Is that clear? And this shift will require a linear number of operations. So what cost me linear time here is not the comparison. It's the rearrangement into an array, which is the condition for the inductive structure of the algorithm, where in the next time around, I will be able to do another binary search. Is that clear? So this algorithm is an inductive algorithm which does repeatedly binary search. For binary search, I need to assume that the input is an array. And to make the input an array, it's where I pay the big penalty. Is that clear? Okay. So, and again, I think that if you ask me, well, where is my main opportunity to teach you more, it's exactly not in what I teach, but in actually raising your level of skepticism and try to fail you and ask you to come back with an understanding of why we made this effort and where we skipped over some steps. Okay, so that's this will be a recurrent theme in the teaching here, in trying to make you understand why we do things the way we do, etc. Okay, so I'll see you next Monday. The TA either already posted or will post homework 1, and from now on we start entering a regime of a homework every week, you know, with a proper time. Of course, nobody wants to put you under unnecessary pressure here, but please be sure to do the homework. And one comment I want to make about it, and I said it already before, the homework carries a very limited weight here because we need to recycle questions here from year to year. And one attitude from students is, why should I bother? It's such a small fraction of the grade. And the answer is that by not doing the homework, you will be what's called a penny wise, pound foolish, because while you will save a few pennies of effort because it may not be worthwhile, when you need to do the exam, then you will be unprepared. So I do encourage you to make sure that you do all the homework, you fully understand it, and don't hesitate to ask first the TA and then me if you have any questions about that. Okay, so I'll wave goodbye now and I'll see you on Monday. Okay, take care, bye.
See you on Monday. Bye.
Thanks, Professor.
Oh, you're welcome, thank you.